Hello and welcome to yet another lecture on basic electrical engineering, paper code ES-EE101. Myself, Prathita Roy, Assistant Professor of Dr. Sudhir Chandra Institute of Technology and Sports Complex, Department of Electrical Engineering. Today my topic is losses in transformer, regulation and efficiency. Lesson objective. After end of this lesson, student will able to distinguish between different losses in transformation and understand the concept of regulation and efficiency. So contents losses in transformer efficiency, condition for maximum efficiency, separation of losses, separation of iron loss, all day efficiency, voltage regulation of a transformer. So losses in transformer. In any electrical machine, loss can be defined as the difference between input power and output power. The difference between two powers, that is the input and the output power, is known as the loss of that particular electrical system. So the total power that is input to an electrical machine or say an electrical system is the combination of both output and losses associated with that system. An electrical transformer is, an, is a static device, hence the mechanical losses like windage and the friction losses are absent in it. A transformer only consists of electrical loss, that is the iron losses and the copper losses. And all these losses of the transformers are dissipated in the form of heat. So the type of losses in the transformer, that is losses in the transformer, are generally iron or the core losses, copper or the ohmic losses, stray losses, dielectric losses. So this iron and the core losses are classified or divided into two parts. One is known as hysteresis losses and another is known as eddy current losses. So the total losses of the transformers are divided into four part, that is iron or the core losses, copper or the ohmic losses, stray losses, dielectric losses, and iron or the core losses is divided into two parts. One is known as hysteresis losses and another is known as eddy current losses. So we are starting with copper loss. The copper loss is occurred due to the power that is wasted in the form of I square R, where I is the current that is passing through the windings and R is the internal resistance of the windings, that is the primary and the secondary winding of the transformer. So when a current that is flowing through a primary and secondary winding of the transformer, depending upon the resistance of the primary and the secondary, the I square R losses, that is the mathematical expression of copper loss, is occurred in those windings. It is clear that the copper loss is proportional to the square of the current, that is I square, and current dependent on the load. It is very much clear that the current that is totally depend on the amount of load that is required from the consumer end. Hence, the copper loss in transformer that is varies with the variation in load. Hence, that is why it is also called the variable loss. So copper loss generally depend on the current square of the current that is flowing through the windings, and as the load varies, the current also varies. So that is why copper loss is known as the variable loss. So that is the total copper loss, that is I square P RP, that is P, that is stands for the primary winding, that is the current that is flowing through the primary winding and the resistance of the primary winding, summation of I square is RS, that is the current that is flowing through the secondary winding. This A stands for, and this is the resistance of the secondary winding. So the total copper loss total, that is the copper loss in the primary winding, summation copper loss in the secondary winding. Now iron loss or the core loss. These losses occur in the core of the transformer and are generated due to the variation of the flux. Due to the variations of the flux, a loss that is occurred in the core of a transformer is known as iron loss or core loss. They depend upon the magnetic properties of the material used for the construction of the core. Hence, these losses are also known as core loss or the iron loss and represented by W suffix I. I stands for iron loss or the core loss. So generally it is depend on the magnetic properties of the material that is used for the construction of the core. That is why these losses are known as iron loss or the core loss, and it is occurred due to the variation in the flux within the core. So we have already seen that core loss. That the core loss have two parts. One is called the hysteresis loss and one is called the eddy current loss. It is the two subdivision of iron or the core losses. So the eddy current loss in transformer, the leakage magnetic flux linked with the conducting parts like steel core or iron body of the transformer, which will result in induced EMF in those parts. That we have already seen that the leakage magnetic flux that is linked with the conducting parts like steel core or iron body of the transformer, which results in EMF will induce those parts, causing a small current within them. So that is the general mathematical formation of core loss, that is WE. That is the eddy current loss. E stands for eddy current loss. That is WE equal to C suffix E Bm square into F square. That is the that is generally known as the eddy current loss of the system. This current is called as eddy current. Due to this eddy currents, some energy will be dissipated in the form of heat. All the energies that is dissipated in the form of heat. Lamination. Now a question will arrive that how eddy current loss can be reduced with the help of the lamination of the core materials. Means when the core materials are laminated, we can able to reduce the eddy current loss. Hysteresis loss. This generally is this hysteresis curve that is already known to us, and this hysteresis loss is due to the repeated magnetization and demagnetization in the transformer core. The energy is lost in each hysteresis cycle. The hysteresis is nothing but the graph that is give us an idea of repeated magnetization and repeated magnetization and the demagnetization. Magnetization, demagnetization in a particular way that is called the hysteresis that we have already known. And due to this, the energy lost in each hysteresis cycle cause the conception of hysteresis loss. So the laws depend upon the volume and the grade of the iron that we are used, frequency of the magnetic reversal, and value of the flux density. So hence the hysteresis loss can be given as W suffix H, that is the loss due to the hysteresis, equal to CH Bm to the power 1.6 into F watts. This is the general formation of hysteresis loss. So hysteresis loss that is totally depends upon the volume and the grade of the iron, frequency of magnetic reversals, and value of flux density. Soft magnetic materials with low hysteresis, such as silicon steel and CRGO steel, are usually used in core to reduce the loss. So, for the eddy current loss, the core is laminated in order to reduce the loss. In case of the hysteresis loss, soft magnetic materials with low hysteresis, such as like silicon steel or CRGO steel, are generally used in core to reduce the loss. So the total core loss, that is W suffix I or the iron loss, is the summation of hysteresis loss and the eddy current loss, that is WH plus WE, where WI is where the hysteresis loss is given by CHBm 1.6 to the power 1.6 into F plus CE Bm squared into F squared, where is CH or CE, that is the in case of the CH it is called the hysteresis coefficient. This is CH, is known as hysteresis coefficient whose value depends upon the material. So for the casting, the value of KH is 0.025. For silicon, the value of CH, that is called the CH, the CH generally known as the hysteresis coefficient whose value depends upon the material. In case of the casting, the value of CH is 0.025. For the silicon, value of CH is 0.001, and the value of and for the silicon steel, and the, the CE, that is generally known as constant, that is depending upon the material. So this is the hysteresis and the eddy current loss, and summation of the both losses are generally known as the iron loss of the particular system. Now another is called the stray losses. The stray losses is due to the presence of leakage field, including eddy current in the tank walls and the conductor. So the leakage law or the stray loss that is occurred, that is due to the presence of the leakage field that cause an eddy current in the tank walls and the conductor. There is a flux leakage and there is the eddy current loss that is particularly seen in this figure. This one called the eddy current loss, and that is dot portion is the flux leakage. So the winding of the transformer should be designed such a way to minimize the stray loss, and that is achieved by splitting of conductors into small strips to reduce the eddy current loss. So we have to split the conductor in small strips in order to treat the strips in order to reduce the eddy current loss, or say the stray loss. Another is the dielectric loss. Dielectric loss occurs in the insulating material of the transformer. That is the insulating material that is known as the oil of the transformer or the solid insulations. Those insulating materials where the dielectric loss occurs. When the oil gets de- deteriorated, when oil gets deteriorated or the solid insulation get damaged or its quality decreases, and because of this the efficiency of the transformer get affected when the oil get deteriorated or the insulation, that is the solid insulation, that damage, their performance or the quality decreases and the efficiency of the transformer is affected. The percentage of these losses are very small as compared to the iron and the copper loss, so they can easily be neglected. This is the general conception of the dielectric loss, which is occurs in the insulating materials of the transformer, like the oil of the transformer or the solid insulation that is provided in the transformer. Now we will come to another part that is called the efficiency of the transformer. So the efficiency of a transformer can be defined as the ratio of power output to the real power input. P suffix O, that is stands for the power output, and P suffix I, that is stands for the power input. So eta, the efficiency eta can be written as mathematically real power output, that is P suffix O, divided by real power input, that is P suffix I. In case of the transformers, practical transformers, if I consider the practical conception of the transformers, there are losses that is associated with this. So the efficiency can be written as output by output plus losses. Input is nothing but the summation of output plus losses. So it can be the efficiency eta can be written as output by output plus losses. So the efficiency is nothing but V2 I2 cos phi 2, that is the output power from the secondary side, by V divided by V2 I2 cos phi 2 plus I2 square R plus Pi is the efficiency, that is the output, by output plus iron losses plus total copper losses. That is the losses. Output by output plus losses, output by output plus iron losses equals the summation of plus the copper losses. These two losses are iron and the copper losses. So this is why the efficiency of a transformer can easily be determined. The efficiency of a transformer, it is nothing but the ratio of real power output by real power input, where input is the summation of output plus losses. We are considering the losses, that is the total losses of the system, that is the iron losses plus total copper losses. So the efficiency can be written like that. Output is nothing but the input minus losses by input. So it is 1 minus losses by input. So efficiency eta can be written as, the efficiency can be written as 1 minus total losses, that is copper loss plus total coal loss, total iron loss plus total copper loss divided by Pi. 1 minus total losses, that is the summation of iron loss plus total copper loss divided by Pi. That is the efficiency can be written. So let us take a power output P0 equal to x into s suffix r cos phi 2. So where S suffix I stands for this one, VI, that is the summation of voltage into current, VI at the secondary side. That we have already seen V2I. Where X is generally known as the fraction, or in other words, we can say that the X is the times for the full load. X is the time, that is the times for the full load, the efficiency is maximum. So that is the portion of the full load for which, or the times of the full load for which the efficiency became maximum. So the total losses, that is WT, the iron loss will remain constant and it will become x square into W total copper loss. X square into copper loss, because copper loss are directly proportional to the square of the current. So total full, that is the total copper loss, that is full load copper loss, equal to x square plus into x square multiplication, x square into W of copper loss, total copper loss, that is the full load copper loss. So the efficiency can be written as, is the output power is a fraction, because current now in a fraction, current, it is called the VI cos phi 2. Now I became some portion of x into I, so that is why output became x SR cos phi 2. SR is nothing but the V into I. So I became some portion. I became, uh, where x is generally known as the, for the maximum efficiency, the load is x time of the full load, because means that I became x of I, a portion of the load for which the maximum efficiency occurs. So that is why it, that is the output x is this part x are cos phi 2 plus wi, and this is become, that is the iron loss, that is remain constant, and this is become x square in into w, means the total copper loss. Because why it is x square, again I am telling that it is x square because the copper loss is directly proportional to the square of the current, and x is the portion of the current or the load for which the maximum efficiency occurs. So let us deal with a problem that is given that a transformer is rated at 100 kVA At full load, its copper loss is 1200 watt and its iron loss is 960 watt. Calculate the efficiency at full load unity power factor, the efficiency at half load 0.8 power factor, the efficiency at 75% of the full load at 0.7 power factor. So it is given that SR, that is the rating of the transformer, that is the multiplication of VI that we have already told, that is the output power. It is 100 kVA that is given. Iron loss, it is given 960 watt, that one, iron loss. And the copper loss, it is given at full load. Copper loss, you just remind that line, at full load, the copper loss is 1200 watt. It is 1200. As the load is changing, the copper loss also changing with proportional to the square of that load. So it is given, that is the kVA rating of the transformer that I have already told, that is the kVA rating of the transformer, this one, V into I is R. So this is the kVA rating is R of the transformer, V into I, kVA rating, that is R. So now we all know this one is the general formation of efficiency calculation. Now at full load and the power factor is unity, means cos phi is unity. So we can write at the full load, it will be 1 into, this is the x part, this is the x part. So at full load, the x value is 1. So 1 into 100 into 10 to the power 3 into 1, that is VA rating from kVA to VA, that is where we are multiplying with 10 to the power 3. And it is given that this is the same thing, that is the output plus losses, that is the iron losses, and this is the copper losses. And at full load, it will be 1 square. So after taking the percentage, it is 97.88%. After multiplying that equation by 100, this one, 0.9788 multiplied with 100, it will give 97.88. Second one is the efficiency at half load and 0.8 power factor. So cos phi become 0.8, and this is become half load, means I became I by 2. So the output also became I, because output is Vi cos phi. So where I became I by 2, so output will become half. So it is now half into 100 into 10 to the power 3 into 0.8. Half into this same thing will be repeated here, output plus iron loss will be remain same 960. Only change in the copper loss. It is given that copper loss, the math in this problem, it is given that copper loss at full load is 1200. So half load it will be 1 half square, that is half square into 1200, that is 0.9694. After multiplying with 100, it is 96.94%. So here this is the main thing is written that here x is half because the load is now half load, so output became half, and the copper loss will become 1/4 of the full load copper loss, but iron loss remain constant. Now at 75% full load at 0.7 power factor, so M became 0.75, so it is, or X becomes 0.75, so it is 0.75 into 100 into 10 to the power 3, 100 into 10 to the power 3 into 0.7, that is the power factor. This is the output is that one, plus 960, that is the iron loss, and the copper loss became 0.75 whole square into 1200, that is the 75% of the full load. So it is become 0.9698 and it is equal to 96.98%. Only the change in the output and also the change in the copper loss proportional to the square of that particular times, that is the x times, or say that, say in case here it is 75% when the half load. In this way the entire problem is designed. So condition for the maximum efficiency. This is the general information of the efficiency of a transformer. For maximum efficiency, the value of ddx with respect to x, ddx of eta equal to 0, and the second order derivative will be less than 0. So if I, from the equation 1, if I take the ddx of n for that particular and do the derivative, we will get that particular equation. This one. So ddx of eta equal to 0, that is given that this part will be 0. If this part will be 0, the entire thing will be 0. So it it is given that this part will be 0 means entire things will be 0. So the iron loss is equal to x square into total copper loss. So the condition for the maximum efficiency is that the efficiency of a transformer for a given power factor is maximum. When it will be maximum? It is clearly seen that this will be maximum when Wi equal to Wut when x equal to 1. So it is given that the efficiency of a transformer for a given power factor is maximum when the variable loss, that is the copper loss, is equal to the iron loss. When those two losses are equal, means the value of x is equal to 1. This is the condition for the maximum efficiency of a transformer when the variable loss, that is copper loss, is equal to the iron loss. So this is the efficiency versus load graph. This is the load along the x-axis. This is the efficiency. This is the maximum efficiency. And corresponding, if I draw a perpendicular line on the load graph, it is the load corresponding to the maximum efficiency. Now the current and KVN rating at the maximum efficiency. So we know that the total copper loss is I2 square into RT2. That is IR square, I1, I suffix 1, R1, R square into RT1. That is I2 square RT2, I1 is 1 square, RT1, and that is I2 R square RT2 and I1 R square RT1 in other words. So the X is nothing but the root over of Wi by WCU total. So Wi became equal to X square I2 R square RT2 W I equal to I2M square RT2. M stands for the current at the maximum efficiency, and at that maximum efficiency R became M and X became 1 because both those losses are equal. So that is why this equation is written as I2M square R2. So current at the maximum efficiency I2M equal to root over of Wi by RT2 equal to I2R root over of Wi by WCUT. That is the total copper loss from that equation. From that equation, I2R, because x square RT2 is the WCUT, total copper loss. That's all. Now I1M, that is the this I2 stands for the secondary side, and I1 that is stands for the primary side, and the current at the primary side maximum current, that is Wi by RT1, is equal to I1R root over of Wi by total copper loss WCUT. So KVA rating at the maximum efficiency is M equal to same, is M equal to SR root over of Wi by WCUT, that is the total copper loss. Total copper loss. So the maximum efficiency can be given as eta m is V2 I2 m cos phi 2, V2 I2 m cos phi 2 plus 2 Wi, because in the case of the maximum efficiency, all iron loss and the copper loss are same. So we can write it W twice of Wi iron loss. So in, that is the eta m, is can be given as the efficiency is x SR cos phi 2 x SR cos phi 2 plus 2 Wi, where x stands for root over Wi by WCUT, and I2M equal to Wi by RT2 root over of Wi by RT2, where x is root over of Wi by W cut. W X is root over equal to root over Wi by, that is iron loss by the total copper loss, where I2M equal to root over of iron loss by resistance RT2, that is, and equal to I2R root over W iron loss by total copper loss. Just putting those values there, it is twice because iron loss and copper loss are same, that is why it is written as twice Wi. And I2M is the maximum current that we have already calculated. So the maximum efficiency at constant loading factor. So this is the general formation of the efficiency. Constant loading factor means x became constant. So if x became constant, that is Wi plus x square total copper loss, that is x square W suffix copper loss total equal to K. So that efficiency eta became this one because this term is replaced by the K. So we can write it 1 by 1 plus K divided by X is R cos phi 2 at maximum efficiency. It will be the minimum part. If eta going to be maximum, this part will be, we are rearranging that particular equation in this way, divided by the, this equation is divided by X is R cos phi 2, and we are getting this equation. In order to find the maximum efficiency, this term will be minimum, and this term will be minimum when cos phi 2 is the maximum. Hence, for the constant load current, maximum efficiency occurs when the load power factor is universal unity, that is called the resistive load. When the resistive load is there in the system, the maximum efficiency occurs when the resistive load is there in the system. When this one is minimum, the efficiency is maximum, and this one is minimum when this part is maximum. This part is maximum is unity when it is the resistive load. So for the resistive load, the maximum efficiency occurs. Now this is the efficiency curves on transformer. So separation of the iron losses, that the iron losses are separated into two corresponding components, that is hysteresis loss and eddy current loss. But the hysteresis loss is this one, WH, A stands for hysteresis loss, equal to CH Bm 1 to the power 1.6 into F watt, and the eddy current loss is C Bm square F square W. So the total loss that is written in this way, but WH, W suffix H, that is stands for hysteresis loss, W suffix E, that is stands for W suffix H stands for hysteresis loss in watt, W suffix E stands for eddy current loss in watt, Bm is the magnetic flux intensity, that is Tesla, and CHB, that is hysteresis loss constant, that is from the value of y-intercept in the graph, and CEB, it is written as CHB and CEB. This total term with this one, it is written as CHB and this is written as CEB. CEB is the eddy current loss, that is the value of the slope in the graph. That is the value of the, that is the graph, that is frequency versus the loss graph, and when that we are finding the value of the slope, that is the tan theta equal to B, will give the value of eddy current loss constant, the value of the slope, and the hysteresis loss is the constant, that is called the value of y-intercept in the graph, that is one A. Is the value of y-intercept in the graph, that is A, will give the conception of hysteresis loss, and the eddy current loss will give the value of, but the eddy current loss will give the value of mm, the eddy current loss is the value of the slope. Slope will give the value of eddy current loss, and this will give the value of iron loss that we have already seen. It's called the hysteresis loss. Hysteresis and eddy current loss and summation of iron loss. So an example given that in a transformer, the core loss is 100 watt at 40 hertz and 72 watt at 30 hertz. Find the hysteresis and the eddy current loss at 50 hertz. So it is given that the iron loss is 100 watt at frequency 40 hertz and iron loss is 72 watt at frequency 30 hertz. So we have to find the hysteresis and eddy current loss in 50 hertz. So the solution is that Pi by F equal to A plus FB. So it is given that 100 by 40 equal to A plus 40B and 100 by 30 is A plus 30B. This is the general formulation that we have obtained from the graph that we have already seen, the general equation. Y equal to mx by c. Here it is Wc by F. So y equal to, this one is mx by c. Mx plus c. Y equal to mx plus c. This one. So from that equation we are finding the A and the B value. So the hysteresis loss at 50 hertz will be Ph equal to A into F. That is 2.1. That is I have found, into 50 is 105 watt. And the eddy current losses at the 50 hertz is E, that is B into F square. So hysteresis loss is directly proportional to the frequency f, and that we have already seen, and eddy current loss is proportional to the square of the frequency. So V value we are found, and we are multiplying with 50 square, it is given that 25 watt. So one will give 105 watt and one will give the 25 watt. Hysteresis got 105 watt, eddy current loss is 25 watt. So from the slope we are detecting the value of eddy current and the hysteresis loss. So now another point is called the all-day efficiency. So computing the efficiency by taking the ratio of ramp power output by real power input is just the performance of power transformer which are energized only during the load condition. The load connected at power transformer are normally at constant level around full load. Distribution transformer are initially by electric board power grid and keep energized for all the 24 hours in a day, 7 days a week, and 52 days a year. The load that is connected such transformer keeps on changing from time to time. In a day of 24 hours, such distribution transformer are subject to full load hardly about 4 to 5 hours. In remaining period, they are only partly loaded. Sometimes they are on low load. That means the iron loss is occurred at constant level for 24 hours, while the copper loss that is occurred in the transformer keep on changing with respect to the change in the load condition. So it is clear that when it is running 24 hours, but they are hardly operating 4 to 5 hours at full load, and the remaining period they are partly loaded or sometimes on no load. So the iron loss will be remain throughout the 24 hours, where the copper loss that is changing with respect to the load condition. So therefore, the performance of distribution transformer by taking into account the energy delivered and the energy consumed by it for all the 24 hours in a day. So the definition given that all-day efficiency of the transformer is defined as the ratio of energy delivered by the transformer for 24 hours in a day to the energy consumed by the transformer from supply system for the same period. So the all-day efficiency can be given mathematically is the ratio of energy delivered, that is kilowatt hour, and O, that is the output power, stands for output, and the energy consumed, that is kilowatt hour, I, that is I, stands for input, multiplied by 24. So it is the ratio of the energy delivered by the transformer in 24 hours in a day to the energy supplied by the transformer from the supply system for the same time period. It is generally known as the all-day efficiency of the transformer. That is the ratio. All-day efficiency is the energy delivered in kilowatt hour, energy consumed in kilowatt hour, divided by energy consumed in kilowatt hour into 24. That is the all-day efficiency of the transformer. So to have high oil efficiency, distribution transformers are designed and constructed with low iron losses. The load at which the maximum efficiency occurs. Wi stands for the iron losses, and W of suffix copper loss total is the full load copper losses. So the energy output that is given by summation of Xi is R cos phi into Hi, where the energy output is generally in kilowatt is given as energy output plus energy to losses. Energy required to meet the losses. That is kilowatt hour input is the summation of kilowatt hour output into 24 Wi plus x square W card Hi. This is known as the all day efficiency summation of x square W card Hi. So now we are coming to another point that is called the voltage regulation of a transformer. So the voltage regulation is defined as the change in magnitude of receiving and sending end voltage of the transformer. It is the change in magnitude of receiving and sending end voltage of the transformer. The voltage regulation determines the ability of the transformer to provide the constant voltage for variable loads. The ability of the transformer to provide a constant voltage when the load varies. It is defined by the voltage regulation. When the transformer is loaded with continuous supply voltage, the terminal voltage of the transformer that is varies. The variation of the voltage depends on the loads and its power factor, that is the terminal voltage of the transformer. So mathematically, the voltage regulation can be represented by voltage regulation equal to E2 minus V2 by E2. So the percentage of voltage regulation is nothing but E2 minus V2 by E2 into 100. But E2 is generally known as the secondary terminal voltage at no load, and V2 is the secondary terminal voltage at full load. This is the mathematical expression of voltage regulation. So the voltage regulation by considering the primary terminal voltage of the transformer is, if I consider the primary terminal voltage, it will express in the percentages V1 minus V1 by V1 into 100. So let us take an example in order to understand the conception of this is the primary side voltage regulation. Example in order to understand the voltage regulation. Let if the secondary terminals of the transformer are open circuited or no load is connected to the secondary transformer, if the, then the no load current will flow through it if the secondary terminals are at the no load condition. If the no load current flows to the secondary terminals of the transformer, the voltage drop across their resistive and reactive load becomes zero because there is a no load condition. So the voltage drop across the resistives and the reactive loads become zero. The voltage drop across the primary side of the transformer is negligible. So let us take that two transformers. Let us take a transformer and where it is loaded at the secondary side. And this is the general equivalent circuit of a transformer is known to us. If the transformer is fully loaded, there is load is connected to the secondary terminal. That is, we have seen that here the first portion is no loaded, and here is an equivalent circuit of the transformer where the secondary is loaded. The voltage drop appears across it. The value of the voltage regulation should be less for the better performance of the transformer. It is clear that the value of voltage regulation should be less for the better performance of the transformer. For the circuit diagram shown above, the following the conclusions are made, that is, the primary voltage of the transformer is always greater than the inverse EMF of the primary side. V1 is always greater than the V1 because from the V1 there is a drop here and we are finding the value of V1. So V1 is always greater than the E1. The secondary terminal voltage at no load is always greater than the voltage at the full load condition, that is E2 greater than V2, because uh, the secondary voltage, terminal voltage at no load, that is E2. From E2, that there is a drop is occur in that particular secondary impedance, and we obtain a voltage V2. So it is always greater than V2, and V1 is always greater than V1 because from the V1 there is a drop is occur in the primary side impedance. So the secondary terminal voltage at no load is always greater than the voltage at full load condition, that's E2 greater than V2. So, by considering the above circuit diagram, the following equations are drawn that I have already told. V1 equal to I1 R1 cos phi 1 plus I1 x1 sin phi 1 plus V1, and E2 equal to I2 R2 cos phi 2 I2 x2 sin phi 2 plus V2. The approximate expression for the no load secondary voltage for the different types of load is for now we are considering the inductive load. So in case of the inductive load, the E2 became I2 R02 cos phi 2 plus x2 x02 sin phi 2 plus V2, or E2 minus V2 became I2 R02 cos phi 2 plus I2 x02 sin phi 2. So E2 minus V2 by E2 into 100, that is the voltage regulation, became I2 R02 x2 into 100 cos phi 2 plus I2 x02 E2 into 100 sin phi 2, where I2 R02 by E2 into 100 is a percentage of resistance drop, and I2 X02 E2 by 100 is the percentage of reactance drop. Now for the capacitive load, E2 became I2 R02 cos phi 2 minus I2 X02 sin phi 2 plus V2. So E2 minus V2 become I2 R02 cos phi 2 minus I2 X02 sin phi 2. So E2 minus V2 by E2 into 100, that is the voltage regulation, will become I2 R02 E2 into 100 cos phi 2 minus I2 X02 E2 into 100 sin phi 2. So in this way, we define the voltage regulation of a transformer. for inductive and the capacitive load. So today we have learned about the transformer losses, that is the different losses in a transformer. We also find the efficiency of a transformer and condition for the maximum efficiency, and we also learn about the voltage regulation of a transformer. Thank you.